lessons. And for the last few years, we have a very important project that's re-evaluation of the nuclear power plant. And indeed, our fellow help us, and that's a great help. And I would like to show graduation to take this opportunity. So I would like to share with you is the seismic retrofitting program in Taiwan. So we have two. One is for public building, that's a school retrofitting. Another one is for private sector, for residential building. And I will discuss with you about why we have seismic insufficient and the problem is pretty severe, and therefore we have these two programs. And then for this talk, I will concentrate more on the technology development to relate to these two programs. So first introduction, that 1999 we have Chihshang earthquake. And as you can see, it is a really huge, strong earthquake. And then the maximum PGA is 1.01 G already. And besides, epicenter is pretty shallow. It's about 8 kilometers. And then very strong and affect Taiwan. Here is the affected zone. So fortunately, that time, we already have a lot of the earthquake observation stations. So that's the reason we take the chance, we measure the seismic intensity. But we realized that time, our seismic demand for Taiwan pretty low. And after Chihshang earthquake, we immediately modify our seismic map and make it higher. But let's look back, the building we already have. So here is the statistic about the floor area of our building in Taiwan, along with the year. So before 1999, we have a lot of building constructed already. Majority of this building is reinforced concrete. And before 1999, we account about 58% the reinforced concrete building. We can call them older RC building because they compatible to the seismic code. So the seismic demand for them insufficient. And besides, this building lacks of the ductile detailing according to the seismic code. So indeed, for this amount of building, we need special attention, maybe through the seismic evaluation and the retrofitting to make sure the seismic safety of this older RC building. So among of them, two types of building I would like to discuss with you. The first one is the school building. So during the Chihshang earthquake, you can see that a lot of school building either totally collapsed, partially collapsed, or heavily damaged. The number of the damaged building account for about half of all the school building in the affected area. So indeed, we need to do something for this kind of damage. And why school building so vulnerable? So let me show you is the typical structural plan of the school building. You can see that is quite classical. We have a classroom, but in between we have a very thick brick wall. And therefore, perpendicular to the corridor is the strong axis of this building. But parallel to the corridor direction is the weak axis. We only have frame. Original, we might have 3 frames. But unfortunately, one frame in the corridor was missing because the standard drawing that time issued out. Their thought is that maybe we should create a free space along the corridor because they might be the playing ground for our students. So they took out, one frame. So we have about only 2 frames. So approximately, I think that we lost about seismic capacity about 30%. And the corridor, cantilever corridor, according to the statistic, that's a story height, 1 story, 2 story, 3 story. That's the majority that we have. But cantilever corridor account large portion. So totally about 60% of our school building, they are with the cantilever corridor. And another building type is our residential building. So here is in the Melong 2016 or Hualien 2018. So we do have our high-rise building and collapse look like this way. So because due to the reason is the soft and the weak first story. Yeah. So why is that? Because in Taiwan, we use the mixed-use city planning. So residential unit above, but the commercial space at base. So therefore, we create the soft and the weak first story. So that's the reason why, for our residential building, we have this kind of strat. So for school building, we issue a project. So that project, after Chihshang earthquake, ENCRE already decided, school project as a top priority for the seismic retrofitting. So we spent about 10 years for preparation, and we determined the strategy, and we developed the needed technology. In 2009, we were fortunate. Our government decided, we should have a national project to start with. And therefore, we execute for 14 years. This project was ended last year, and the total budget account for US dollar about 4 billion. So the method we use, commonly, we are using RC jacketing. We make the column size larger. So that's original, that's a jacketed column. Or we can add a piece of shear wall, in between the column. And, but the shear wall, sometimes they block, the lighting and also ventilation-wise. We change our strategy. Some of them, they use the wing wall. It means that we add, 2 small pieces of wall pier and connecting with the column, make the shear strength of the column stronger. Yeah. That's a typical retrofitting method that we have. And for this project, we have 4 phases. So we send the student for field investigation and find out how many school buildings that we have. So about 27,000 school building. But before, constructing before the 1999, and we say, okay, if for this kind of old RC building, but occupied by student and teacher, we send them to the seismic evaluation. So we have preliminary evaluation and the detailed evaluation. So then we can, cut some of the volume out, and then with the seismic insufficient school building, we send to the seismic design, and then retrofitting construction. So the project issued to 2022, we believe we already retrofit, all this amount is about 10,000. So 10,000 school buildings through the engineering measure to increase the seismic capacity. So account with 27,000. So our covering rate about 37%. So yesterday, Doniki talked about the recent earthquake that we have. So this is Dongli Junior High School. And indeed, the surface rupture is obvious. But we do have part 2. This is a school building. So therefore, our earthquake for the rupture cutting through this kind of school building. But this school building retrofit already. So we check, after the earthquake, this building still stand, but suffer a lot of structural damage, such as the column, shear failure, and we retrofit shear wall in here, but still we have shear crack and the wing wall retrofit, and you see severe damage. But we consider this still effective because our target is to try to avoid the collapse. So this retrofitting, school building, subject to, the rupture of the fault still stand. And I believe this is a good evidence that this project indeed is effective. And we also have some international cooperation. And our first partner is with Thailand. So with Professor Panong in AIT and also with Professor Sutet. So here is a photo indicate the building in the north part of Thailand. So school, classroom in the second floor, but the first floor for student as a playing ground. So you can see this is a soft and first story. So our Thailand partner, they decided to use in the current injecting. And in the year 2021, and they finished about 3 school buildings, and quite beautiful. So we only retrofit some of them, but they require to make the other column has share the same size, so you look more uniform and more present. And our second project is with Indonesia and Professor Elwin in the ITB. So in Indonesia, majority of the school building is the confined masonry. So then ITB, they decided, to use the ferro cement retrofitting. So they put, the wire like this and then spread the concrete back. But during the retrofitting, they found out some of the column is lack of the foundation. So in the meantime, they put the foundation back. I think this increased the shear capacity quite a lot. So this year, in May, they finished 4 school building already. So I think that they all look beautiful, and the teacher and student, they can enjoy more pleasant environment and much safer. And let me introduce the retrofitting for residential building. So we have a large amount of residential building. So we cannot retrofit them all. And besides, it's very difficult because if you so many owners, very difficult for them to reach consensus. They would like to have a retrofitting. So we are thinking maybe we do that only for the soft and the first story. We retrofit here. Simply remove the seismic deficiency. That's a stage 1. But at least we can have life safety. But later, if they want to retrofit the whole building, and can be done. So here is one case in Hualien. That's a residential building, 6-story high. And the first story, they use that as a parking lot. So that's a soft first story. And for the first story, we add a few pieces of the shear wall. And then we check, the deficiency of the soft and first story can be removed, and pretty cheap. Another example is in Taiwan, and the first story is a market. So they would like to have, during the operation, the market can still open, for business. And therefore, the strategy this time, we are using external frame. So we put the external frame like this and make the building stronger, and they can remove the soft first story problem. So for these 2 projects, we use different technology. Because school building is a low-rise building, but the residential building may be medium-high to high-rise building. So to check out the seismic insufficient, so maybe we should use a different method. So for low-rise building, we are thinking maybe using the pushover analysis. But we are facing a problem, because for our school building, you can see that the concrete strength, our statistics show, originally we would like to have 21 megapascal, but the concrete strength too low. So it means the shear strength is low. But unfortunately, the longitudinal reinforcement, the steel, originally we designed with 275, but our statistics show that the mean value already 391. It means the fracture strength is higher. So we have a higher fracture strength. We have lower shear strength. So we have the shear critical element. So shear critical, I think that Professor Giacomelli already recognized as a non-ductile, member. That's a serious problem. But we need to find out what's the solution for this. And for that shear deficiency, we have other problem because for this old RC school building, the stirrup is widely spaced. And we lay out the seismic, hook, for this column. So that's the reason why the detailing is not good. And therefore, the shear critical indeed, for column and also for shear wall. So during the earthquake reconnaissance, we can see that the short column, we have shear failure, and the typical column, shear failure as well, and even for the shear wall, and subject to shear failure. So therefore, we need to solve this kind of problem. And then we categorize into two parts. Maybe we can have a single D region. It means low rise, maybe low rise shear wall or short column. And the force transfer is a bottom shape strut, only one strut. And then the failure criteria we set as a crushing of the concrete. So that's an observation in the laboratory. But if you're dealing with slender shear wall, such as DBD, so we have a D region stress concentration and maybe D region at top. But in the middle, stress can be uniform distributed, and we call that DBD. For the shear transfer, they were using the fan-shaped strut, so it's slightly different. So we developed the softened strut tie model. So this is a beam current joint. So you can see that the shear should be transferred directly to the opposite point. And then we can use diagonal stress flow, to model the stress transfer. It's not uniform, but with equilibrium, we're using strut tie to check it. And compatibility, we're using more compatibility and to establish the relationship within the strength field. And for constitutive, the concrete, we are using crack reinforced concrete phenomenon. So seeing the strength will be higher. But if you have a crack and you want to transfer the compression force, the average strength will be lower. So that's our constitutive. And we define our failure criteria as a concrete crushing at the end of the concrete strut. So based on this model, we track the available literature. And indeed, for D-beam, for Cobell, shear wall, and external beam current joint, internal beam current joint, they all singly D region member. So the failure will be concrete crushing. And indeed, we use this model to check. And the test value divided by our model, if equal to 1, it means accurate. But larger than 1, it means test value is higher. The model is conservative. And the average ratio for the strength is around 1.2, and the coefficient of variation is around 20%. So I think that can be used because the failure is due to concrete, variation should be larger. If failure is due to steel intention, of course, variation will be smaller. And for shear strength of the fan shape, so I think that the concrete crushing may be using the same model as a softened strut tie model, but in here we have a shear tension failure. But the ACI code developed, for several decades. So they have a lot of, slender shear wall, and they found this equation is useful. So we believe, for the fan-shaped strut, if you want to have sufficient tensile strength, make the concrete strut can have equilibrium in both ends, right? So maybe they need the tensile capacity. If insufficient, then we have the shear tension failure, and we simply adopt the ACI formula. So we use this concept to check the available tests. So this is a short column, intermediate, high to depth ratio, or typical column. And also shear wall with opening. And we check the shear strength. Indeed, it's still, valid. So the mean value still around 1.2, and coefficient of variation, we can have about 20%. But if we want to locate the exactly, the critical member and where it failed in sequence, maybe we should use more advanced, analysis. So then we decided maybe we can use is a nonlinear static analysis to capture the critical location. Therefore, the retrofitting, the smaller the better. And we use the pushover analysis. We find out the base shear and the roof displacement. That's a capacity curve. And we use the single pendulum to convert this curve into capacity spectrum. By choosing performance point, we can find out the AP. AP is the performance target ground acceleration. And we use this value to check with our code requirement. And therefore, we decided is seismic safe or not. So since we want to perform the pushover analysis, we have to establish the backbone curve for all the column. So it means the short column, shear wall, typical column, and the wall with opening. The shear backbone curve, we have to establish because not so many literature available to check out this shear capacity. But the fracture is okay. So we develop the backbone curve for the shear critical member. So in Anchorage, we perform the test, and we also invite a lot of university professors to work with. So we can use the strong floor to test, static test. We can use the shaking table to test the shear strength and also the shear wall. And our goal is that once we have the test and the major data, we have to establish what's the model, because we would like this to be used and to be included in the school retrofitting manual. And about the backbone curve for shear critical member, indeed, we already solved for short column with the intermediate depth to span ratio, and also the typical column and the shear wall with opening. So the blue curve is the experimental data, and the red dot is our predicting model. So within establish this low diffraction curve, a very important concept we adopt is collapse. Yeah. Because you can see from this photo, subject to shear failure already. But since you have the actual load, and therefore there was some shear friction, maybe can sustain the column without gravitational failure. So we can present using this. You have fracture failure and you have the plateau. But if you reach the delta S, maybe your shear failure look like occur. But you can still push it without collapse of this column. And therefore, you have larger displacement delta A, then you can claim maybe they lost the gravity load carrying capacity. So I think this model was developed and first recommended by Elwood and Meili in the year 2005. So the delta S, the delta A being published already. So we saw this kind of information. We are very happy. And we want to use immediately. So therefore, in Anchorage, we established a cooperation for Anchorage, UC Berkeley, and UBC, University of British Columbia. So we test using the shaking table. 2007, 2009, we already have our test result, and we verify that two equation, and therefore we immediately use in our school retrofitting manual. So in Taiwan, we start to use the collab information starting from 2009. But in America, maybe ACCCS 41 will be 2013. So we are kind of for 4 years. 4 years is crucial for our school project because we started our school project at 2009. And also in Taiwan, we have a lot of brick wall, and therefore cannot be neglected. So we also test, brick wall with the opening, and here is the test value, and the model established in Anchorage, and look like this. But we are not the inventor of this model. The model was developed in National Cheng Kung University by Professor Hwang and his PhD student Chen Yixing. I think this model is very good, and therefore, we perform the test to further verify that. So in Anchorage, we have the menu, and the menu for school use starting from 2008. But along with the time, we have a revised version. So right now we already reached about the T-SPA, our 4.0. So we have 5 addition already. That's used for pushover analysis. Then let me talk about the nonlinear time domain analysis. So we all understand if we have a high-rise building or medium high-rise building, cannot neglect is the seismic response. They have the higher mode effect. And therefore, this kind of response cannot be captured by pushover analysis. And therefore, maybe we should shift to nonlinear dynamic analysis to capture the insufficient of this kind of building. So therefore, in Anchorage, we already find, because we have a lot of the earthquake data. So then Anchorage already published that the platform of input motion selection for Taiwan. So engineer can select the earthquake input already. And then for hysteresis, we recommend to use the pivot, hysteresis model. It means that maybe we choose a pivot point here. And for the unloading stiffness, they are passing through this pivot point. And therefore, you can see the degradation of the unloading stiffness. And also reloading, we choose another pivot point. And then you can see along with the larger lateral displacement, we can represent the pinching effect. So this model, we already developed for column and also for shear wall. So for example, here is a column. We put 2 fracture hinge in here, 1 shear hinge in here. The alpha and beta is to choose the pivot point. But for fracture type, fracture hinge, we use in this parameter equation. It relates to the actual load, longitudinal reinforcement of the column, and the transverse reinforcement of the column. But for shear plus hinge, we have another 2 equations. So here is, we check with the data. But of course, we use a nearly method to find out that equation. But it seems that we can capture the fracture failure, fracture shear failure, and also the shear failure with severe pinching. So we have a test set up. We want to check how good is our model. So let me introduce one frame. So we have shear critical in the middle. You can see the spacing of the hoop is pretty wide, and the leg of the cross tie. But the other 2 columns is the fracture control, and therefore we have a better detailing for the reinforcement. So this is the test result. So you can see that in the middle, probably shear value. But the other 2 columns is a fracture column. So then we can model, using the ETAPS. We would like to engineer to use that more friendly. So we put 2 fracture hinge and 1 shear hinge in the middle. And then the capacity curve we already developed in the school project. So that's a backbone curve. And the hysteresis rule, we're using the pivot model. And then for simulate the test result, you can see that the base shear we can capture really well, but the displacement not so good. But we can use the fiber model. So we try already. If we combine with the fiber model for that 2 fracture column, and the result can be better. And it turned out that this is the result that we have. But indeed, the shear value and the stiffness we can capture really well. But the displacement for the fracture column, maybe we still need to put more effort. So let me draw my conclusion, is that we have 2 projects. School project starting from 1999 and ended last year. And we have about 10,000 school building already retrofit. For residential building, and we simply want to remove the soft and first story. And we started in the 2018. And now we have 6 years, we have 50 cases being established. So we think that for people, if you have illness, you will use the scanner, the MRI, to find out what's your health condition. But in building, indeed, we do have the health index. We have the IO in here. We have the life safety. We have the collapse prevention. So we need to check out the health index for our building. And we believe our effort for the low-rise building, we established a backbone curve relationship, and we call T-spot. But we can use ETAPS or SAP or the program we developed in Ankry, that's a PISA 3D, and then we can find out the building health. But for high-rise building, instead of backbone curve, we still need the hysteresis. And right now, our effort is in the T-star. And I think that these two technology, they can help us to protect Taiwan better. And I think that it's a group effort. It's not me alone. So I would like to thank the Ankry for the long-term support, and then we can have this kind of technology development. Oh, thank you very much.